Okay, thank you for the introduction, and many thanks to the organizers. I think we all share the satisfaction to be part of this meeting, especially to be in this framework. So many things. Okay, I have a big cold and lost half of my voice, so I'm sorry for the vocal expression. Okay, and I'm aware also that it is the last talk of a quite relatively long day, and that the topic is maybe more focused on PDEs analysis than on probabilities. But anyway, you will see. So this is a joint work with Marta Leocata, who was in Scuola Normale Superiore di Pisa, and who's now in LUISS in Roma. Okay, so the outline of the talk is the following one. So I will address some few simple questions relative to the modeling of chemical reactions, some standard things. So introduce the stochastic system of reaction diffusion equations that we are interested in. So give a collection of some elementary facts, and then explain what is our main result and some element of the proof. Okay. Okay. So about the modeling of chemical reactions, there are two main ways, two different approaches. So one probabilistic approach to the description of chemical reactions through either jump process, either on the family of particles or directly on populations. And there are some deterministic models. So that in most of the case can be deduced from the probabilistic model in the large population limit, which are system of ordinary differential equations or PDEs if we take the spatial displacement into account. Okay, so there are also some questions related to these approaches to modeling. So obviously the large particle limit. So I give few references on this topic. E.T. Kurtz, Oschlager, and a recent work by Lim, Lu, Nolan. And regarding the deterministic modeling, which is described by systems of reaction diffusion equations, there are different questions, but one of the main questions is to investigate how the structure of the system leads to possible global existence of solution, and eventually to a description of the large time behavior. So I will give some references on the subject in the course of the talk, but I mentioned already a survey by Michel Pierre, which contains a lot of material on this subject. Okay. So I like to say a few words on the probabilistic modeling in a very simple framework, and I will consider this binary chemical reaction. Actually, I will consider this reaction all along the talk. So we can, if no displacement is taken into account, so you just study the chemical reaction in itself, we can describe this reaction by a Markov process on the size of the population of each species. And the evolution of the process is done by jumps with rates that are proportional to the size of the population that enter into a given reaction. Okay, so the reaction are here. And so if we look at the generator of the actually rescaled process, we rescale by n, we obtain this this ln here. Okay, so so the L is a vector. A is a vector with 4 components because there are four species. Okay, and L is a vector corresponding to the forward reaction. So you consume A1, you have a minus, and S3, so you have a minus, and you produce A2 and A4. Okay, and the L corresponding to the backward reaction is just minus the forward L. Okay, and the rate here appear again here. Okay, so now let's just look at the large n limit of this particle system just by looking at the generator. So I make an expansion in a Taylor expansion in a generator at order 2. Okay, so sorry, I go back actually. It's very simple. Here you expand, so at first order you will cancel the n here, capital N, with a 1 over n here. Okay, so this is what we get here, where f of a is this function, sum of L of the rate here. And at second order, of course, you get the second derivative of phi, and you have the factor 1 over n. Okay. So at first order, we recognize the generator associated to standard ODE, okay, which is dA over dt equal f of a. Okay, so if I just write the component of a, this is the f, and if we expand to second order, we recognize the generator associated to diffusion. So this is approximation diffusion, and we have an explicit expression of the noise here. With some coefficients, you see, so there is the L of the forward and backward reaction, and the square root of the rate. Okay, so just remember momentarily this expression. Okay, and here you see there is a sum over two instances here. So we just need actually 2 independent Wiener processes to describe the noise. Okay, so essentially this is the most probabilistic part of my talk, and then I will speak a lot of PDEs. Okay, so I hope you will be sensible to the problem we regard. But first, also, I'm aware it doesn't work, of course. So it's an animation. Sorry, it doesn't work. Alors, je regarde juste quelque chose quand même. C'est ouvert avec quoi ça? Bon, tant pis. Okay, bon, because we're all waiting for the cocktail dinner party, but okay, let's go through the talk. Okay, so motivated by the previous modeling considerations, we look at the following equation here. So this is basically a system of PDEs because we take spatial displacement into account now. The Fi is exactly the reaction term corresponding to this chemical reaction here, this binary chemical reaction. And here we have diffusion terms, which corresponds to displacement of reactant by diffusion, each having its own coefficient here, kappa I. Okay. To give some more details on this system. So the kappa are positive constant for the talk. Actually, it may be it may depend on x or and t, but it's not really. It doesn't really matter. And here, nu is a small constant, which corresponds to the large n in the large population limit. Okay. And regarding the noise, how is it built? So the noise. So here we have a finite number of Wiener processes here, and the coefficient of the noise. So if you remember what I said three slides back, it should be something like this. The coefficient of the noise. Okay, something like this. However, we cannot really consider this kind of coefficients because we need to have at least an invariant region for the PD to ensure that the AI stay non-negative if the initial data is non-negative. Of course, the AI are in a way chemical concentration, so it should be non-negative. Okay, so we have to assume that the coefficient of the noise vanish when the AI vanishes. And so actually this structure here, we just prescribe it asymptotically as a growth condition on the coefficient of the noise. Okay, so we have this growth condition here, okay, which is relatively consistent with the reaction we have here. Okay, and so what is the central question here? Central question is about the existence of global smooth solutions. So if we start from smooth initial data, which are non-negative, and in any case I work with non-negative solutions. So does the system admit global smooth solution? And when I say smooth, it's smooth in X. Of course, in T we are limited by the noise. Okay, so this question is related to a certain number of problematic. Of course, the same question in the deterministic case, okay, which has actually has been the object of a lot of works. I will explain this. And actually, the fundamental thing when you study the existence of global smooth solution is to get an L infinity bound. The threshold is really L infinity, and of course you can understand this because once you get an L infinity bound, you kill the nonlinear aspect of the equation. Okay, so you are back in the world of linear equation, to say things in a rough way. And you can control everything. Okay, so really the whole aim, if you consider solutions a priori solutions, is to get an estimate on the L infinity norm, the supremum norm. Okay, and so this is why I point out the second item here. This question here is related to the question of L infinity bound in scalar parabolic equations, so whether deterministic or stochastic. Okay, so I will spend some time on this aspect of things also. And maybe I should have pointed out a third theme, which is a question of, simply of regularity in scalar stochastic parabolic equations. There are in particular some works of Arnaud and Martina of Manova, which we relied on. Okay. Just to go deeper into this description of the state of the art, regarding the deterministic reaction diffusion system with this kind of quadratic nonlinearity, there are a bunch of works in which the existence of a global smooth solution is established. And so in particular a work by Goudon-Wasser in 2010, restricted to dimension d less than 2. So later it was extended to all dimension in this paper. And there is this approach is based on the DiGiorgi's iteration scheme. So I will get back to that later. And there are different approaches with different techniques which lead to the same results. Okay. In particular here, you use the maximum principle on clever transformations of the system. Okay, so unfortunately, in a way, what we are able to adapt is this approach, which is restricted to dimension d less than 2. So our result will be given in dimension d less than 2. Okay. And so regarding the second item, the question of supremum estimates in stochastic parabolic equation, well, there has been a lot of work. I will not give all the lecture of all these items. So just one thing, basically supremum estimates in stochastic in SPDs are quite tricky because L infinity is not too smooth space, so martingale arguments do not work. But here we are considering parabolic, stochastic parabolic equation. So what drives the thing is a parabolic character of the equation. Okay. Okay. So here are some references, but I will get back to this later. Okay. So this is in a way relatively boring, this list of references. Now I go back to math just to present you some elementary facts related to the deterministic system. Some elementary facts that I will show you if you exploit them a little bit more, allow you to get some results. First, there is an important and basic point. It is the fact that if all diffusion coefficients are equal, things are simple. Okay, if you consider the case where all the coefficients are similar, you see here. So for the deterministic equation, you can just add up the 4 equations of the system. Okay, so the right-hand side cancels out, of course, because of the alternance of the sign is alternating here. So you get this simple heat equation here for the z, which is the total mass, the sum of the AI. Okay, and so if you just apply the maximum principle on z and take into account the fact that AI is non-negative, you get a bound on the AI. Okay. So this is the first thing. In the case, I go back to the general case where coefficient diffusions are distinct. Actually, you can do the same thing. Just add the 4 equations of your system here. So similarly, the right-hand side it cancels out here. And you get this equation. Now the coefficient the diffusion coefficient k here. Actually, it's not really a diffusion coefficient because it is inside the Laplace operator. And this k is given as the convex combination of the kappa I, and the coefficients here are the AI over z. So they depend on space and time because AI is a solution. Okay, so you don't know much about this k, but I will come back to this later. For the moment, a simple conclusion you can draw from this equation by integration, since we are in the periodic setting, is that you get a control on the L1 norm of the total mass. Okay, but L1 in the world of PDs is not a lot. Okay. Actually, you can do a little bit better by exploiting the fact that for this equation you have an entropy, and this is simple to see also. So you just multiply the equation by the log of AI here. and say you integrate over space and time. Okay, so if you introduce this primitive of the log here, you sum up, so you get a control on this quantity, which is the total entropy, which is non-negative. Here you have a good term coming from the diffusion. And here you have a term related to the reaction terms, and which has a good sign. So if you use the property of the log, you get this term, and since the log is a non-decreasing function, this whole quantity here is non-negative. So with a minus sign here, it has a good sign. So you have an entropy inequality. Okay, and so it means that actually you have a control not on not only on the L1 norm of the AI, but also on the L1 log L1 norm. So it's better than L1, but not extraordinary either. Okay. Now I think it does not work also. No, it does not work. Bon, sorry. It was a nice picture, but anyway. So it's just to say that this is the last part of my talk. So I think yeah. Okay. So the cocktail dinner will come soon. So I will give the main result and describe the main ingredient of the proof. Okay. So basically, what we prove is the following thing. So we work in dimension d less than 2. And what we show is that if the coefficient nu, I hope you remember, nu is a coefficient in front of the noise. So if this nu is small enough, and when I say small, it means small compared to a quantity that depend on the dimension and the diffusion coefficient, but not on the size of the initial data, for example. So if this smallness condition is satisfied, then actually we can establish this kind of control on the L infinity norm of the solution if it is defined up to a blow-up time tau. Okay, and so actually it means that the blow-up time is just plus infinity. So actually the solution is globally defined. Okay. Okay, and I will explain some ingredient of the proof of this result here. So there are three main ingredients. So first, the entropy estimate, which I explained in the deterministic case. So now, what happened in the stochastic for the stochastic system? So if you remember, this is the entropy equation for the deterministic equation. When you look at the stochastic system, you get an additional term, which is the Ito correction here. Okay, and maybe I shall return the system actually. Okay, and remember that the coefficient of the noise satisfies this growth hypothesis. Actually, so actually here. So we have to control this term to keep the benefit of the entropy for the system. Okay, and we are able to do this essentially by exploiting this term, which generally is dropped out, to control some of the term coming from the Ito correction. Okay, so this is not that surprising. Actually, here we don't need the nu to be small. Okay, so after stable estimate, we get a control on the entropy, at least in expectation, and by standard arguments on martingales, we can upgrade this to the control of the moment of the entropy. Okay, so this is first ingredient, relatively simple. The second ingredient is an L2 estimate by duality. So I explain things in the deterministic setting. Remember that when you add up the equation in the deterministic setting, so forget this term, the right hand side cancels out here, and you get this equation which has not a good structure because you have the Laplace of kz. A good structure in PD would be the divergence of k times the gradient of z. Okay, but this is not the case here. A priori, it's not a good structure because k is just measurable and bounded from below and above. And because remember, k is a convex combination of the k per I here. But there is a simple trick which is to look at the dual equation to this one, and the dual equation here is this one. So now the k is outside the Laplace operator. Okay, this is a dual equation, so this is a backward problem here. And so we can add a source term and just impose a trivial final condition here. Okay, and for this equation we have a maximum regulatory result, which means that you have an L2 estimate both on the dt, on the partial derivative and the Laplace of the unknown here, controlled by the L2 norm of the source term. Okay, and from this maximal regularity result, you get an estimate on psi. And if you work by duality, so you test the equation in Z by the psi, actually you can get this estimate on Z here, the Z being the solution to this problem. Okay. So we had first an L1 estimate and a L1 log L1 estimate. Now we have a L2 estimate on the AI. So that's better. Okay. So actually, this L2 estimate by duality, you can do it on Z, which is not the sum of the AI, but the sum of the AI log AI. Okay, because you also have an equation on this kind of quantity. So it means that actually you are able to prove L2 log L2 estimate. Okay, and in the deterministic setting, this was, for example, exploited in this paper to get global existence of weak solutions. Okay. Okay, so this is the approach in the deterministic setting. So how do you do in the stochastic setting for this stochastic system? Well, actually, the L2 estimate by duality is possible, but in that case, what you have to consider as a dual equation is a backward parabolic equation. Okay, of this form, say. Okay, and the good news is that actually, in the world of backward stochastic equations, things are in a way simpler than for forward stochastic equations. Okay, so it's not very difficult to get estimate on this psi here. So actually, we use in particular this paper by Du Tang, and from the estimate on the dual equation, we deduce some estimate on the primal forward equation in the stochastic case. Okay, so actually the idea to use a backward stochastic equation to get an estimate, we had used it with Arnaud and the student previously, and that was in a way the starting point for this study, the possibility to apply the same trick here. Okay, so from this considerations here, we can prove an L2 log L2 estimate in this context. Okay, and actually it's here that we need the nu to be small. I do not enter into the details, but it is where we need the diffusion coefficient nu here to be small enough. Okay. And the third ingredient is DiGiorgi's iteration scheme. Now I think that if you are not specialist of this question, maybe you will find this a little bit far from your actual preoccupation, but this is really what is crucial in the proof. Actually, DiGiorgi's iteration scheme was devised to get some L infinity estimate on solutions to parabolic equations. It was one step on the way to the Hölder regularity, which was actually part of the more general scheme to get regularity of certain nonlinear variational problem. Okay, so that's why sometimes one speaks of DiGiorgi, Nash-Moser approaches, but actually the three of them are relatively distinct. Okay, so here we use the DiGiorgi iteration scheme, and the basic idea is to modify the entropy here by introducing truncates here. So this is the positive part. So you just see what happens when AI is above the threshold Xi here, and all the game of this kind of technique is to prove that as a function of Xi, the functional here you consider is decaying fast enough, and actually so fast that at some point it vanishes. Okay, and when it vanishes, if it vanishes, you know that AI is dominated by this threshold. Okay, so you get a supremum estimate here. Okay, actually we use the entropy, the modified entropy, which brings some technical difficulties. At least if you compare this to the classical approach for parabolic equations here by DiGiorgi, where the starting point is to use the truncated energy just being the L2 norm. Okay, so it is quite simpler. Okay, and I will just give some more expand on this framework. So now I forgot the system and I just go back to a discussion on basic scalar parabolic or stochastic parabolic equations. Okay, so the basic estimate you get by DiGiorgi's method or Moser's approach, if you know Moser's approach, you get this kind of result. So you look at a parabolic equation with a coefficient diffusion k here, which may be irregular. Okay, because actually it comes from a nonlinear problem, so the k may be a function of u. But you know that it satisfies this bound from below and from above. Okay, and if the right-hand side here is sufficiently integrable, so it is in L mu for mu greater than this 1 plus d over 2, then the u is in L infinity. Okay, so this is the classical L infinity estimate for parabolic equation. Okay, and so as a preliminary work to this analysis of systems of reaction diffusion equation, we worked on the extension of this kind of estimate for stochastic parabolic equations. Okay, so now I add noise in this linear equation. This is a linear, and what we want to prove is this extension of the deterministic result. So here for the G, for the variation here, we need a regularity L2 mu. Okay, we need twice more integrability here. This is not surprising. Okay, and we get some moments here, and the threshold for the integrability stay 1 plus d over 2. Okay. So actually there are various proofs of this result. For example, by Dariotis guess, by Moser's approach, and also a partial result by Su Wang Wang where actually they start from mu directly equals to plus infinity and satisfying deterministic bond. Actually, here I forgot an expectancy. Huh? It may be random, this one. Okay, I forgot the expectancy here. So with Marta, we did an extension of this paper to get the right threshold for mu by De Giorgi's approach, and I just mentioned another approach, still by duality. So to go back to a duality trick, because we like duality tricks. And the idea, so, is to work on the dual equation. So here I describe things in the deterministic case. So the dual equation is this one, and to prove this gain of regularity. So if you have a terminal condition which is L1, your solution psi is LR, with LR which can go up to this exponent, which is a Fujita exponent. So this is my quotation of Japanese mathematicians here. Here we recognize the Fujita exponent. So we have this gain here from L1 to LR. Okay, and by duality, if you exploit this gain here, you get also the gain from L mu to L infinity. Okay. Okay, so this result is by Bocardo-Galouette. Okay, so actually it's true in a more general for a nonlinear equation. But the duality tricks uses the linearity of the equations. Okay, and of course, if we want to extend this in a stochastic framework, we do the same. What we use is a backward SPD again. And actually, this is an approach which is much nicer than the approach by De Giorgi's truncation techniques. I must say, it's really simpler. But unfortunately, in the study of the system here, we have to use the De Giorgi's truncation approach. Okay. Okay. So these are the main ingredients of the proof. So I will stop here. Just with some open questions. So, of course, can we prove the global existence of smooth solution in dimension d larger than 2? I didn't discuss the question of boundary conditions. We are in the periodic setting. It's not very natural from a modeling point of view. And actually, this is a serious question to consider different boundary conditions, really. Maybe you wonder about this probabilistic to derive this system. What I did is to start from the probabilistic description of the chemical reaction by forgetting about the spatial displacement. Okay, just for a static problem. And we get this kind of noise here. But actually, if you extend the analysis to now a system of particles that may move by independent Brownian motion, actually what you get is space-time white noise at the end when you do the diffusion approximation. And actually, if you really consider space-time white noise, I don't know what you can do. Okay, and of course, there is a related questions. When you look at the system of reaction diffusions, this is a pattern formation. Okay, if we refer to the original paper by Turing, and the influence of noise, has for instance been studied by these people, the influence of noise on pattern formation. Okay, so I stop here, and it will, in the name of the organizer, I can welcome everybody to the cocktail dinner to come soon. Okay, santé and kanpai.
Okay, do you have any questions? Commenter? Okay.
If you prescribe with a prescribed noise, can you just show us a typical well-posedness result you obtain? What regularity exactly?
With a prescribed noise?
Well, when you give a noise, how do you define the solution? A bit naive question, and then what precise regularity do you get for the solution?
But actually, we start from you can define a weak solution, okay? But we don't do that. What we do is that we define smooth solution up to a stopping time when it's easy to be smooth, okay? Actually, the stopping time is defined in terms of the L infinity norm. So the regularity we have is typically the solution is in a space like my exponent may be wrong, but something like LQ omega C0t, and we have here a Sobolev space, okay. Okay, and here the M and P can be arbitrary, and Q can be as high as we want, okay.
Thank you.
But this, I have a question which I think is related to that, but you have some, in order to that you in an infinity bound rigorously prove, don't you need some regularity on the initial state or the solution?
Ah yes, the initial state.
Yeah, but so you have some conditions on NMP so that, for example, it's no. My question is.
The initial state is C infinity on the torus. It's smooth. Yeah. Okay. Yeah.
Just one question. So you had this new less than some constant, the in front of the noise, and if it's larger, is it going to blow, or is it, or you don't know? I mean.
No. No, I don't know. I don't know. Actually,
I mean, when I say blow, just you have this L infinite bound.
Yeah. No, we don't know. We don't know. Actually, blow up in reaction diffusion systems can occur, even if you have some favorable structure. But whether when nu is large, it may happen. No, really, it's not an easy question. No, we don't know.
And maybe another. So if you the condition you impose on the noise is very general, but whether if you have some kind of reversibility from a microscopic system, can you deduce? So that would mean the sigma I is specific, but can you deduce from that a general statement which would be possibly independent from the mu?
When you mention reversibility, I think about possible stationary states, but
yes, some invariant measure which would exist by general principle. I mean, which would meant to tune everything to have it. Okay, just a random question, but
yes, but actually this is also maybe the first question to ask if you want to consider a space-time white noise. But no, I don't know. I don't know for this system. This is indeed it would be indeed useful for sure, but we don't know. No.
Any other questions? Maybe one question. So
yes.
You mentioned that as occupations, lifetime behavior and pattern formation. And can you explain which kind of long-term behavior can you expect?
This is a little bit related to this question. No, similarly, we don't know. I don't know what kind of large time behavior we will get here. But at least for the deterministic system here, this is not a deterministic system that shows up pattern formation. The long time behavior of the deterministic system is simply convergence to constant 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 state. Okay, so at least we don't expect pattern formation for this kind of system.
So other system.
Yes, for example, the one I mentioned here is different. It's not the same system.
Thank you very much. So let's thank speaker again.
Thank you.